Now that we've learned about limits, we can start kind of opening the doors to a lot of other topics in calculus. The first one that we're going to be looking at is called derivatives. Now, first of all, when we talk about derivatives, it would be good to have a notation to represent derivative. So we represent the derivative of a function, and in this case we'll say the derivative of the function f as f prime of x. So you can see it written as f prime of x. Or you might also just see it written as f prime. Sometimes you also see it written as y prime. A little bit more rare notation is this capital D for d sub x, for derivative of x, derivative with respect to x. So these are all different functions, or derivative of functional notations that you'll see. So now that we have the definition of a derivative, or at least the notation of a derivative, let's kind of start talking about what derivatives are. Derivative basically represents change, and there's change occurring all around us all the time, everything we do. Time is changing, the speed is changing, how fast I write, how fast you listen. These are all rates of change. And so because everything is changing all the time, derivatives have a lot of applications that we're going to be bringing up. So another thing that a derivative talks about besides change, well, not besides change, but in addition to change, is it basically gives us the instantaneous rate of change. And remember, that was one of our problems that we had in our last unit. We couldn't figure out the instantaneous rate of change very easily. And we're going to kind of go back to that idea of secant lines here in a little bit. So it's the instantaneous rate of change of your function f. So f of x is your function with respect to the independent variable x. The dependent part of this is f of x, so the independent variable x. So if we knew a value for x, or I randomly selected a value for x, I would plug it in, and f of x would be dependent upon that value. Now we use limits not only to define the derivative, but also to develop some efficient rules about derivatives. So this first section, we're going to kind of use the longhand way of finding derivatives to show how derivatives are calculated and found. And then we'll learn some shortcut rules for that. But it's going to be important that you be able to do problems where you're using the limit definition of the derivative. And you'll see the differences here in a little bit. So we talked about how a derivative is the instantaneous rate of change. Probably one of the most common things we use the derivative for is the slope of the tangent line. Remember, this was one of the problems that we ran into in the last unit as well. We wanted to find the slope of the tangent line, and we want to be able to find it at any point along a curve. Now, a lot of times the best we could do was a secant line, and then we'd start talking about limits and approximate that tangent line. But this is one of the big definitions. It's the slope of the tangent line at any point along the curve. And this is really important to know. Make sure you know the derivative, again, is the slope of the tangent line at any point along a curve. So if we were to draw a curve, let's get my picture back up here, we could go ahead and talk about the slopes of the tangent lines. So on this particular curve, my slopes of my tangent lines over here, whoops, I didn't get very straight. This would be a positive slope of the tangent line. And we can see over here we'd have a positive slope to the tangent line. And actually, as we look at this function, I can see this would also be positive, this would also be positive. So along this part, we can see we have that positive sloping tangent line. Now here on this middle segment, you can see that I have a negative slope to my tangent line. So a lot of times you can look at a picture and kind of just by inspection, try and figure out what's going on at the tangent lines. Now something interesting happened. I switched from a positive slope to a negative slope, and then from a negative to a positive. Something occurred right at these points where that change took place. And these points are of interest to us. This is when the slope of the tangent line equals 0. We like to know where the slope of the tangent line is 0. Something important is going on there. In this particular case, I can see that it's a relative min. Over here, I can see that it's a relative max. So over here, when I have the positive slope tangent lines, that would mean your first derivative, f prime of x, is greater than 0. Over here where I have a negative sloping tangent line, f prime of x would be less than 0. And of course over here, f prime of x is greater than 0. Here, this purple line, f prime of x equals 0. That's where my first derivative, my slope of my tangent line, is 0. So these are all different things that we're going to kind of get used to talking about as the slopes of the tangent line. Now because I have a positive sloping tangent line, I'm kind of making a mess and running out of room here, but this is the same as saying that the instantaneous rate of change is positive. Remember, rate of change, ROC. So the instantaneous rate of change is positive. And here the instantaneous rate of change would be negative. Here the instantaneous rate of change would be positive. So there's a direct connection between the idea of the slope and the instantaneous rate of change. Now let's go ahead and review back just a bit about secant lines. Now if we were to talk about a curve, and then on that curve we want to start developing the idea of that secant line. And then when we have the secant line, we want to look at getting closer and closer to a particular point on that line. We can go ahead and define a few of our variables here. So let's go ahead and call this our value a. If we put a in, if we plug a in, we get f of a out. So the height here is f of a. And then what I want to do is somewhere over here, let's go ahead and plug in an x. So this is some variable x, and as I move over here, here's my point. Moving across, this would be the height f of x. So if I were to find this secant line to connect these, hopefully I can do a better job at drawing a straight line here. What I can do is if I would like to know the slope of the tangent line at A, I could just move this point a little closer and a little closer and a little closer and keep calculating these slopes of tangent lines as I get closer. And then pretty soon, I'll get so close that I'll get 2 points that are so close together that it'll estimate that perfect slope between 2 points will be the same as the slope of the tangent line at that particular point. So what ends up happening is x gets closer and closer and closer to a, and as x gets closer and closer to a, f of x gets closer and closer to f of a. So let's go ahead and write that out in a formula form. The slope, m represents slope, the slope of the secant is the change in y. That's the change in my vertical, so that would be f of x minus f of a all over x minus a. So again, change in y over change in x. So this is just the slope formula written for this particular problem. So that's the slope of the secant line. Now, the slope of the secant line is interesting, but that's really not what we want to get out of this. We want the slope of the tangent line. So how could I find the slope of that tangent line? Well, that's just the limit as x approaches a, meaning x gets closer and closer to a, of the same function. Well, you can see the problem here then is x gets close to a, this denominator gets closer and closer to 0, meaning they're closer and closer to 0 units apart. So this idea of taking the limit will give me that slope of the tangent line. Now this is at a particular point A. Okay, so in order for me to actually calculate through this, I would want to find that particular value of A. M of secant, the slope of secant, is also your average rate of change. Now remember, ROC is rate of change. Now your slope of your tangent line is your instantaneous rate of change. And that's really what we want to be able to look at more than an average. We want to see what's happening, as you're driving across the state or you're going up and down the hills. What's going on at a particular time, not what happened over the average of the trip. Now, if you notice, once we find the slope, I also have 2 points. I have a and f of a and x and f of x. I could write the equation of a line, or the equation of the tangent line. So let's go ahead and talk about the equation of the tangent line. There's many different ways to find this, but basically you need to know the slope of the tangent line and then any point on the tangent line. So I'm going to use the slope of the tangent line, and I'll use the point, let's use a and f of a. And the reason I'm going to use a and f of a is that that's where I want to find the tangent line. I want to find the equation of that tangent line that's perfectly tangent at that point. So this would look like y minus f of a, so y minus y1 is equal to m tangent x minus a. Now this again is the equation of the tangent line with this slope at the point a, f of a. This is called the point slope form, and a lot of times once I get the point slope form I like to write it in slope intercept form. So we should probably review some of that terminology in case it's not familiar. This is point slope form. It's y minus y1 equals m times the quantity x minus x1. It's called the point slope form because I use a point x1, y1 and a slope m. Now a lot of times we like to take this and solve it for y, and then I get the slope intercept form of a line. And this one will be familiar with you. It's y equal mx plus b. There's another form that sometimes comes up. It's not as common, but it's called the general or the standard form of the equation. And it looks like ax plus by plus c equals 0. That's basically taking this equation and moving everything to the left and setting it equal to 0. So usually with the a, the b, and the constant, we like to have this alphabetical, and we usually don't like fractions, so we would multiply through to clear any fractions. So these are the three types of equations of lines. We usually start with point slope and move across some of these, but if you ask for something in general or standard form, I want you to be aware of what that is as well. So let's go ahead and look at a problem, and you need to get pretty handy with these and be able to use your algebra when you're trying to find the instantaneous rate of change at a particular point. So for this example, let's consider the function f of x equals, let's use a position function. So let's use f of x equal negative 16x squared plus 96x. So this is a position function. That should kind of look a little bit familiar to you, that negative 16x squared. So f of x equals negative 16x squared plus 96x. We want to have a secant line. We could kind of talk about that if we wanted to, but more importantly, we want to find the slope of the tangent line. At the point 1 and 80. So x is 1, f of x, f of 1 is 80. Now this would be the same as finding the instantaneous rate of change. And again, ROC is rate of change at 180. Now this is not an interval, this is an ordered pair. So this is a parabola that opens down. So we can kind of think about this as a curve sketch if we want to. Now I'm not exactly sure how high this will go, but I just want to get a general idea of this. So here it would be the point, let's say 180. So what I'm trying to find is the slope of the tangent line at that point, one that just skims that curve. So I want the slope of this tangent line at that point. So let's go ahead and go and look at some formulas that we had from up above. So here's the formula we want to look at. The slope of the tangent line is the limit as x approaches a of f of x minus f of a all over x minus a. So we are going to do this by finding the slope of the tangent line is the limit as x approaches a of f of x minus f of a all over x minus a. Now before we'd have to find 2 points, a point here, and then we get closer and closer, and we'd use a table and numerically look at this. But this gives us a quick little way to do this type of problem. So what we have here for our problem, we have f of x equals negative 16x squared plus 96x, and we have a equals 1, because I have a value of 1 here. So let's go ahead and calculate this out. M of tangent equals the limit as x approaches 1 of f of x, that's negative 16x squared plus 96x, minus f of a. Okay, now we have to put up parentheses here. This is probably the most common point to make a mistake, is to forget that you have to subtract the entire function evaluated at a. So this would be a negative 16 times 1 squared plus 96 times 1 all over x minus 1. Remember, it was x minus a and a is 1. Okay, so let's go ahead and keep simplifying. Limit as x approaches 1. Now you can see that we have a problem here as x approaches 1 because 1 minus 1 is 0. So I'm hoping that in my numerator this will simplify quite a bit. So here I have a negative 16, 1 squared is 1, and then I have 96 times 1. So 96 minus 16 would bring us to an 80. So I have a minus 80 here. And this is all over x minus 1. Well, if I plug 1 directly in here, I have a negative 16 plus 96, which would be 80. 80 minus 80 is 0. This is 0 over 0, which is indeterminate. Now remember from our previous unit, indeterminate means to do more work. So the more work that we're going to do, hopefully, is to factor this. Okay, so let's keep working on this one. Let me skip down to here. So the slope of that tangent line and if I want to factor this, I think the best thing for me to do would be go ahead and pull out a negative 16. And the reason I want to pull out a negative 16 is I like that leading coefficient to be positive if possible. So if I factor out a negative 16, I'm left with x squared. Now I'm factoring out a negative, so a negative times a negative would give me a positive. So I have a negative, and then next 16 times, gosh, 16 times 6 is going to be way too high. Let's think, 96 divided by 6. 96 divided by 6 would be 6. Yeah, 6 isn't too high. That would work. And then minus, I factored a negative away, so this would be a plus 80. Wait, 16 times 5 is 80, so this would be a plus 5. And this is all over x minus 1. Now, I'm still not ready to take the limit because I still would have an indeterminate form. So the limit as x approaches 1, I have a negative 16, and then this numerator factors further into a product of binomials. This would factor into x minus 1, x minus 5. Now you can see that the good thing has happened here. The x minus 1's cancel. And now when I take the limit, this would equal negative 16. When I plug a 1 in here, 1 minus 5 is negative 4. And negative 16 times negative 4 is 64. So that would be the slope of my tangent line is 64. It's also my instantaneous rate of change at x equal 1. So my slope of my tangent line would be f prime. That's how I represent slope, would be my first derivative evaluated at 1 would equal 64. Now there's another notation that I didn't bring up before. I better run up and add that to the list. It's called dy dx. There's actually quite a few more notations that we'll see, but I want to add dy dx to our list here because it is pretty common. Now you can take multiple derivatives, and we'll talk about that in some later sections. So sometimes you'll even see like doubles and triple primes, and we use some of that information to help us curve sketch and to find some interesting things about curves. So one more notation that you might run across. I just want to make sure you're familiar with it. So there's our slope of our tangent line. I want to find now the equation of the tangent line. Well, we can definitely see that it was a positive sloping line, so that makes sense. So equation of the tangent line at, and it was 180. Now sometimes you'll be given the 1 and then you'll have to come up with the 80 on your own. So you don't have to be given the y value. In this particular case they did. So what we would do is we'd start with y minus y1 is equal to m times x minus x1, the point slope form. So this would be y minus 80 equals m, which is 64 x minus 1. So if they asked for this equation in point slope form, this is where I would stop. But if they want it in slope intercept form, I would go ahead and distribute the 64. So I'd have 64x minus 64. And then I would solve for y, and I would do that by adding 80 to both sides. So I have canceling occurring here. I have y equals 64x. There's that slope again, 64. And then 80 minus 64 would be 16. So this would be my answer in slope-intercept form. Now we can go one more if we want. And I could move everything across to the left. I could subtract over that 64x and subtract the 16. And I'd have a minus 64x plus y, because I'm going to write these in order, minus 16 equals 0. Now usually you don't like your leading coefficient to be negative, so we'd multiply through by a negative here, and I'd have 64x minus y plus 16 equals 0. So this is our general or standard form. So no matter what form you're asked to write your equation in, you need to make sure you know on point slope. That's because you're given a point and a slope-intercept because this gives you your slope as 64 and your y-intercept as 16. And this is called your general or your standard form. So it's good to be familiar with all of those. So what, again, we found was that instantaneous rate of change, or the slope of the tangent line, and then the equation of the tangent line of that curve at that point. Now there's an infinite number of slopes and an infinite number of equations of tangent lines over that entire curve, but this is the only equation of the tangent line at 180. So you should be able to find any of the points on the line with this equation, or any of the tangent lines with this equation. Now the formulas that we came up with before for the slope of the tangent line and the slope of the secant line over an interval, those are these two equations right here. These are going to be important to know. And again, average rate of change and instantaneous rate of change. Now this was over the interval from, let's say, a to x. And you can see on our horizontal axis, that's what we had from a to x. But what if I just wanted some incremental change, meaning a to some value slightly larger than a? So what we can do is we can come up with a new set of equations to describe that, but it's really for no other reason than I want a small incremental change above a. So instead of defining a whole other point, I'm just going to say, what would happen if we just moved a little bit above a point? So again, we're going to look at rate of change. So this particular equation will be used under different circumstances, so that's why we're developing it. So the rate of change, actually let's put in the average rate of change to start with. So the average rate of change on the interval, let's do a to a plus h. So this is an interval, this is not an ordered pair, notice the brackets, is the slope of the corresponding secant line. So let's go ahead and write out what that would look like. So the slope of the secant line would look at f of a plus h minus f of a all over, it would be the change in y over the change in x. So what we did is we said, okay, what would I get if I plugged a plus h in? That's f of a plus h over f of a, and then the change in x would be a plus h minus a. So a plus h minus a. Well, if we rewrite this a plus h minus a, you can see the a minus a cancels and you're just left with h. So this would be a way that I could talk about that secant line at point A, and then I would just look to see what that incremental change was. What did I add to that? Now we have another equation that we can use then for the instantaneous rate of change using that same setup. So A plus H. So again, we're just looking at a very small change above A, or we could even do below A as well. So this would be equal to the slope of the tangent line would be then the limit as H goes to 0, meaning we want to go 0 units above A. We want to approach 0 units above A. So this would be f of A plus H minus f of A all over H. So again, the other example, we had a value as x approaches A. Now what we're saying is I want to find the slope or the instantaneous rate of change at A and then some very, very small value above A. So it's not an ordered pair, it's just saying a small value above that. So these equations we would use under different circumstances. So let's go ahead and look at an example where we would use this. So for this example, let's find an equation of the tangent line. And of course, to find the equation of the tangent line, we'll just actually start by finding the slope. So let's go ahead and find the equation of the tangent line using our new equations. So let's use the slope of the tangent line equals the limit as h approaches 0 of f of A plus H minus f of A all over H. So we're going to use this. And let's go ahead and use f of x, and let's use a square root function this time, square root of 3x plus 27, and then let's go ahead and do this at point, actually let's just do at x equal, let's do one a little bit different here, at x equal 3. Okay, so if we wanted to, we could go back to our other method as well, but I want you to see how this works out too. So to find the slope of the tangent line, of course, we never drop any of our notation. We drag all that along. We look at the limit as h approaches 0, f of A plus H. That would be the square root of 3 times A plus H plus 27. So this is f of A plus H. And then I subtract f of A. So that would be subtracting the square root of 3A plus 27. And this is all over H. Now, if we plugged H in as H approaches 0, I would get 0 over 0, which is indeterminate. And of course, indeterminate means to do more work. Well, we have quite a bit of work here to do. So let's go ahead and simplify this a bit to get started. First thing I want you to be aware of is you cannot combine these radicals. They're not alike. So I can't push both of these underneath the same square root sign. So let's go ahead and simplify. This would be 3a plus 3h plus 27 minus the square root of 3a plus 27 all over h. This looks like it's worse, not better, and you're right. It's much worse. What I'm going to do is I'm going to multiply top and bottom by the conjugate. So 3a plus 3h plus 27 plus root 3a plus 27, and then the denominator will be the same. Now what makes this the conjugate is this plus sign right here, because up here I had a negative, conjugate would switch to a positive. Now the reason we do this is when I multiply this out, the first outsides and insides lasts. I'll get rid of some of the radicals on the inside and outside. So if I took root 3a, because you're taking all of this times all of this, and h times all of this. So if I took root 3a plus 3h plus 27 times root 3a plus 27, it equals 3a plus 3h plus 27. So that would be my firsts. Now my outsides would be a positive radical with the binomial, radical trinomial, and then my insides would be the negative, so those would cancel. And then my last, I'd have a negative here, and times the quantity, root 3a plus 27 times root 3a plus 27 is just 3a plus 27. Now the important thing to remember here is that it has to subtract through that binomial. So as we're simplifying, I have my slope of my tangent line. Limit as h approaches 0, 3a plus 3h plus 27. I'm going to distribute the negative, minus 3a minus 27 all over h. Now when we go through this process, it's always our hope, if we did our work correct, that everything will cancel except what has h's in it, and that's exactly what happens here as well. So I'm left with that limit of 3h over 3h, and of course the h's cancel. And when you're doing your handwritten homework, make sure that you show all these steps. Don't skip any steps, because what the deal is with the handwritten homework is you're basically trying to communicate your thought process. So you have to write down your thought process. So the limit of 3, the limit of a constant is just a constant. So I get 3 here. So this is my slope of my tangent line to that graph at x equal 1. So now I want the equation of that tangent line. So I want the equation of the tangent line. So the equation of the tangent line, I need the slope, which is 3, and then I need an ordered pair. Well, the ordered pair, if you look back up, was x equal 1. Oops, went too far here. No, it was x equal 3, sorry. It's x equal 3. And then to find the y value, remember f of 3 is equal to the square root of 3 times 3 plus 27. So f of 3 would equal 27 plus 9 is the square root of 36, which is 6. So this would be the ordered pair 3, 6. Okay, so y minus y1, y minus 6 equals 3 times x minus 3. So if you're asked to write your equation in point slope form, you're done. This is point slope form. But if you have to put it in y-intercept form, we would distribute y minus 6 equals 3x minus 9. I'd add 6 to both sides. And I'd have y equal 3x minus 3. This would be your slope-intercept form. Now it's called slope-intercept form because the slope is given by 3 and the y-intercept is given by negative 3. So even though I'm working with a radical in this case, I can still do the problem. I just have to remember my techniques that I learned in the last unit of determining limits. And again, the first thing you should always do is plug in, and then if I get an indeterminate form, I need to do more work. If I get something that's undefined, then I know my limit doesn't exist. Well, this has been a lot of work. I've done 2 problems, and I've only found equations of tangent lines at a single point for each of these. So this was at x equal 3, and my other one was at x equal 1, I think. So what we want to think about is, what if I wanted to do this for a lot of points on the curve for that instantaneous velocity? Wouldn't it be better if I came up with the derivative, that definition of a derivative, not as giving me one number after all of this work, but giving me an entire function? So let's go ahead and look at the derivative as a function. This is our big definition. This is our big takeaway for this. The derivative of f is the function f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is really important to have memorized. You're going to be using it a lot, and on homeworks, a lot of you know some of the shortcut rules for derivatives already because you've had some exposure to calculus, and you're welcome to use the shortcut rules to check your answers, but I will be looking for this work. If it says find the derivative using the limit definition, you have to use the limit definition if you want credit for that type of problem. You can definitely check it with the shortcut rule, but you need to use the limit definition when asked. Now, This is only true under particular circumstances. This is only true provided, first of all, the limit exists, which totally makes sense because if the limit didn't exist, then the derivative wouldn't exist, and x is in the domain of f. So what this means is I can't take the derivative where a function is undefined. So if I have a vertical asymptote on a function or a hollow point, I can't take a derivative there because it's not defined in the domain there. Now, if the derivative f prime of x exists, really then what we say then is that x is differentiable at f, or f is differentiable at x. Okay, if f is differentiable at every point on an interval, we say it's differentiable on that entire interval I. So it's important to talk about that differentiability over an interval, but let's go ahead and just get used to this derivative as a function. This is called the limit definition of the derivative. And again, you're going to want to have this memorized because we're going to be using it often. So let's go ahead and find our derivative using the limit definition. So find the derivative using the limit definition. Now we have all of our old same strategies that we learned in Unit 1 for taking a limit. So don't forget those, multiplying by conjugate, simplifying. Now all of this works with trig functions as well, so I don't want you to forget about the trig functions. So let's go ahead and look at, we've looked at some polynomials, we looked at a radical. Let's go ahead and look at maybe a rational expression. So let's go ahead and look at f of x equals 4 over x. So the limit definition of the derivative, f prime of x would equal the limit as h approaches 0, f of x plus h minus f of x all over h. So I'm going to write the generic first, and then I'm going to populate this equation with the 4 over x. So f prime of x equals the limit as h approaches 0. F of x plus h would be 4 over x plus h. Now notice the plus h is in the denominator, it's not up top, minus my original function, 4 over x all over h. Now if I took this limit right now, this would be 0 over 0, which is indeterminate. And of course, indeterminate means to do more work. Well, the more work that we know how to do from our previous sections is we know how to find a common denominator. Now I don't drop any of this notation. Again, on a test or your handwritten homework, if you drop any notation, you're going to be losing credit because we don't want to lose sight of exactly what I'm finding. So do not drop notation. Do not drop your limit notation either. So finding a common denominator here, 4 over x plus h minus 4 over x. For this piece, my common denominator would be x times x plus h. So here I'd multiply top and bottom by x. Here I'd multiply top and bottom by x plus h. So I'd be left with 4x minus 4 times the quantity x plus h all over x times x plus h, and that's divided by h over 1. Okay, I'm going to keep simplifying. Do not drop your derivative notation. Do not drop your limit notation. And again, the tricky part here is to make sure that this negative gets distributed. So I'd have a minus 4x minus 4h all over x times x plus h. Now remember, when you divide by a fraction, you multiply by the reciprocal of the second fraction. So this is 1 over h. Now we've already talked about what we want to have happen here. We want everything to cancel except stuff that has h's in the top. And these definitely do cancel, 4x minus 4x. And you can see that you're going to be using some serious paper here for a lot of these problems. So the limit as h approaches 0. I'm left with a negative 4h. And then I'm just going to scoot this h into the same denominator because I'm multiplying the fractions, so I can do that. xh times x plus h. Then I can cancel the h's. And I'm left with the derivative equals the limit as h approaches 0, negative 4 over x times x plus h. Now remember, we have to take the actual limit now. We've done so much work, and sometimes you lose sight of what you're supposed to do at the end, so that's why you don't drop your notation. This h is going to 0. Well, if that h goes to 0, what I'm left with then is f prime of x equals, the limit is gone, negative 4 over x times x, or x squared. So this is the general derivative of the function 4 over x. This is the slope of the tangent line. At any point along f of x equal 4 over x. Except, remember, x cannot equal 0. And the reason x cannot equal 0 is my function is undefined at 0. So this is an example of how we can find that derivative. Now it's really important that you simplify completely. You don't stop. You know, you have to keep going until it's simplified completely, and then the limit is much easier to take. So that again is the derivative, is the slope of the tangent line at any point along the curve. It's also the instantaneous rate of change at any point along the curve except at x equals 0, because at x equals 0 the function's undefined. So let's go ahead and talk about why we have x cannot equal 0 there. So let's consider another function. So for this function, let's use f of x equal x squared minus 15x plus 56, all over x minus 8. So my question here, is x differentiable, or is the f of x differentiable for all values of x? Let me make sure I have f of x here. Is f of x differentiable? Okay, so let's go ahead and have a look. The first thing I kind of look at with this function is I think, you know what? This looks like to me that x cannot equal 8. The reason it cannot equal 8 is because if I plug 8 into my denominator, I get 0 back and I can't divide through by 0. Now you might look at this and say, well, wait a minute, I think that might factor out. X minus 8, x minus 7. But when you determine the domain of a rational expression, you determine the domain first, and then you do any simplifications or canceling. So you're right, this does simplify to f of x equal x minus 7, but I still have the original restriction that x cannot equal 8. So it is not differentiable at x equal 8 because I have a hole in the graph there. So it's not differentiable at x equal 8. So that's an important thing to keep in mind. Now this would be true for any asymptotic function as well. Okay, let's go ahead and do one more example just because I love doing limit definition of the derivative, and then we can wrap up this lecture. Okay, let's start a new sheet of paper, or I guess I'll be able to use a little bit of this. We're going to use a lot of paper for this one. So we want to find the equation of the tangent line. In order to find the equation of the tangent line, you need to have a slope, of course. So find the equation of the tangent line. To f of x equal, let's do 3x squared minus 4x. And let's do this at x equal 1. Now sometimes you're given an ordered pair. For our example, I'm just giving you the x value of 1. We can graph this with a calculator, and you'll be graphing some of these in your homework, and you just need to make sure that you graph not only the curve but the tangent line as well when you're done. But if you want to double check your work, let's go ahead and have a look at what 3x squared minus 4x looks like. So we'd go ahead and hit clear, go to y equal and clear that out. So 3x squared minus 4x. So if we take a look at this, we might have to adjust our window. We won't have to adjust it too much. I'm going to, actually I'll just leave this one alone. 3x squared minus 4x, and we're interested in what's going on at x equal 1. So there's going to be some sort of a tangent line right through here. But I need to find the equation of that line first. So I'm trying to find the equation of the tangent line right here. So we need to find our slope first. So our slope is f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, or I could also use this one. F prime at 1, because I know my value here is 1, equals the limit as x approaches 1 of f of x minus f of 1 all over x minus 1. This will give me a value, a number. This will give me a function, and then plug in x equal 1. So I could do either one of these equations. This gives me the number of my slope, the value of my slope directly. And this gives me an entire function up here, and then I can take that function and evaluate it at x equal 1. So you can use either one of these. It doesn't matter which one. I think the second one is probably a little bit faster, but I like doing all the algebra, so I think I'm going to do the first one. Okay, so let's get started. F prime of x is equal to the limit as h approaches 0 of f of x plus h. So that would be 3x plus h quantity squared minus 4 times x plus h. And what I'm doing is I'm plugging directly back in up here. That's my f of x plus h minus f of x. Now make sure you have up some parentheses or curly braces here. So I have 3x squared minus 4x, because I need to make sure that that negative distributes. Now if that negative sign doesn't distribute, everything won't cancel like I need to have happen, and I won't be able to find my limit. So let's go ahead and keep looking at this and simplifying. Lots of algebra going on here. Now it's tempting to just drop all of this f prime of x in the limit notation, but really you don't want to do that, because remember at the end you have to actually take the limit. And we were going to do so much work here that you might forget what you dropped. So you drag all of this along with you, and I'll always be looking at that when I'm grading your handwritten homework and your exams. So this would be 3 times x plus h times x plus h minus 4x minus 4h, and then I'll distribute this negative minus 3x squared plus 4x all over h. So again, do not drop any of that notation. F prime of x equals the limit as h approaches 0. So for this piece, I have the 3 out front, and then if I FOIL this out, or if you like the box method, you can do that as well, I'd end up with x squared plus 2xh plus h squared. And then a couple of interesting things happen here. The minus 4x and the plus 4x cancel, so that's a little bit helpful. But I still have this minus 4h minus 3x squared left. This is all over h. Next step, we'll distribute through that 3, and again, don't drop this notation. So I'll have 3x squared plus 6xh plus 3h squared minus 4h minus 3x squared all over h. So this is working out well, because remember we wanted everything to cancel except what had an h in it, and the 3x squared and the negative 3x squared do cancel. And I'm left with f prime of x equals the limit as h approaches 0. And if you'll notice here, I have an h in each term, so I'm going to go ahead and factor out that h. This would be the wrong way to do this, to say, oh, there's an h here, 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 and here. That's not how they cancel. You cannot cancel terms, you can only cancel factors. So the right way to do that is to factor out the h. And I'll be looking for that particularly in your work, so please make sure you're showing that factorization. So you have 6x plus 3h minus 4 all over h. Now, h divided by h is 1. That's the correct way to show that simplification, and I'm left with f prime of x equals the limit as h approaches 0 of 6x plus 3h minus 4. Now, as h goes to 0, this entire middle term goes to 0, and I'm left with f prime of x equals 6x minus 4. Now, those of you who know the shortcut rules, you can do a quick little check, and that derivative does make sense using your shortcut rules that we'll be learning in a little bit. But you can't go directly to the shortcut. You have to be able to show your work in between. So what is this? What did we finally just find? This is the slope of the tangent line, or the instantaneous rate of change. So the slope of the tangent line at any point along f of x equals 3x squared minus 4x. Now 3x squared minus 4x is a polynomial, so it's defined for all real numbers. So there's no points where this is not differentiable. Now remember, we wanted the equation of the tangent line. And I think we said at x equal 1. Okay, so if x equal 1, let's rewrite our original function again. 3x squared minus 4x. F of x, which is our y value essentially, is 3 times 1 squared minus 4 times 1. So this is 3 minus 4, or negative 1. So my ordered pair, so my point that I'm working with is at 1, negative 1. Now what about my slope? Well, my slope is f prime at 1. And I'm choosing 1 because that's my x value. Now my slope is up here, 6x minus 4, so this would be 6 times 1 minus 4, which is 2. So my point is 1, negative 1, and my slope is equal to 2. So I'd go ahead and plug this in. So this would be y minus a negative 1 equals m times x minus 1. Y minus a negative 1 would be a positive 1, so y plus 1 equals 2 times the quantity x minus 1. This would be point slope form. And it just depends on what you're being asked for in your solutions. On your handwritten homework in your test, make sure that you look to see how the equation is supposed to be written, and if none is given, you can be able to use any of the forms of the equation. If we wanted to keep simplifying this, I distribute through the 2 and subtract 1 from both sides, and I get y equal, canceling occurs here, 2x minus 3. And this is the slope-intercept form. Of the equation. Now, y equal 2x minus 3, I can plug into my calculator. So let's go ahead and y equal, let's go to our second equation, and that was y equal 2x minus 3. Now if I graph this and it doesn't look like a tangent line, I know I have a mistake. There's my curve, oh, there's my tangent line, so that does look good. So let's go ahead and snap that into our lecture. And so what the problem I was given was to basically come up with the equation of this red line. The blue curve is the function that I was given to work with. And then the red line is the equation, or that actual tangent line. So the ordered pair was 1, negative 1. That's this point right here. 1, -1. And we can see that the slope of here is definitely positive. And so this makes sense. It looks like it's a good picture. So if you want to graph these to double check your work, you can. Again, on a test you won't have that ability, but it's a good idea to be able to start visualizing some of these so you have an idea of what it should look like. As usual, if you have questions, please let me know. You're welcome to take a shot of your work or a screenshot of the problem and ask any questions. You also have your Pearson Connect. And after our first exam, we'll also be introducing another option for getting help, and that is online office hours. So good luck, and please let me know if you have questions.